Hello everyone. Good afternoon again to Concept Colliders. So we are going to delve into what demonstrations mean, both in math and in the sciences. It's a very broad topic, as always here. This topic is within an even more general topic called rigour, which is one of our main topics in for the next SEMF summer school this July in Valencia, which by the way is going to be both online and in person. So even if you cannot come to Valencia, there's that option. But in Valencia, in person is way better. So as always, I'm going to begin saying, okay, I'm Alejandro, I'm Alex, I'm going to be the moderator of this colloquium. And in general, the idea is that we keep on topic. I'm going to help into that for us doing that. There's going to be a relatively strong moderation for that. I'm going to more or less limit the timing of the interventions for all of us to be able to speak, because many of us love talking a lot of time, me included. And of course, if I will give priority to the ones in the call for the interventions, but I will also we will also be attentive to the YouTube chat. So first of all, secondly, now the workflow. So after a very brief introduction, we are going to go through two sections, maximum half an hour, 40 minutes each one. And at least the idea is to go through several of the main sub-questions that I prepared. And then I'll open, at the beginning of each section, I'll open the floor for interventions of this question. So yeah, you can see the timer there. There's several timers, more than the ones here, because maybe some more people join later. But yeah, and yeah, let's begin. So basically, this topic is amazing because it covers so much, from machine learning, including to the history of philosophy, to mathematics, and in every field in science, this is very relevant. This is a question that comes from, like, we can track it back to not only Western philosophy like Hume, Kant. It also appears in Taoist and Buddhism. I'm not going to get into that, but yeah. So the thing is that it's quite universal. We try to do that. We try to get concepts that are universally enough, and culturally diverse enough. So first of all, one of the concepts, at least in the Western, not only, I mean, I'm going to use terms used in the Western tradition, but I insist these kind of debates have also existed beyond that, and that's why I included them here. But the Western concepts in this dichotomy that I'm going to mention is, in mathematics specifically, realism slash Platonism. That's two terms that is used in one of these currents, and the duality, and the other term of the duality is constructivism, which is usually within intuitionism. This dichotomy is quite interesting for what demonstration means, because specifically in mathematics, the first current, realism slash Platonism, has proposed that proving something means at least usually needs proof by contradiction. So at least knowing that something, to prove that something exists, at least you have to demonstrate that it not existing cannot be possible. And that usually has been defended because there's something assumed here. A mathematical world, independent from the human mind, is assumed. So there's some kind of very neat structure beyond what we usually can access, and but regardless of whether we can access it or not. Then, if the world, that kind of mathematical world, is very well structured, pre-structured, then a proof by contradiction is quite easy. It's quite valid. We can be considered quite valid for us to just consider that something exists, because if If it cannot not exist, then that's it. But then there's the other tradition that considers, like such as intuitionism, that considers that mathematics is built up by humans and our specific minds and so on. And within this current, there's this thing called constructivism, which says, okay, we since precisely because mathematical objects are mental objects, we have to explicitly specify them. We have to explicitly build them, because if not, we cannot trust that they exist. So, in some sense, constructivism is more skeptical about a more has less immediate trust on the apparent existence of something in the mathematical world. So this kind of debate is quite interesting for many reasons. But first of all, I was just instead of just a question, I would just want to open the floor for you to comment on this duality. It has a lot to do, of course, with the concept of demonstration, and I can tell you some thoughts later about why I think this is even related with like computational modeling neuroscience, at least philosophically. But first of all, let's open the floor for you all to just comment on this duality, on any aspect of this duality. Okay, it's not
Which of the dualities do you mean, Alex?
yeah, like the demonstration, like two kind of philosophies of what's necessary for demonstrating the existence of mathematical object. And in those two streams of thought, historically there's realism / Platonism and constructivism, which is usually within the intuitionist tradition. So
Okay.
one just proof by contradiction, and the other requiring more explicit construction of the mathematical object.
Mm-hmm.
So basically, for example, basically the first one is quite common in mathematics, and it doesn't require that much of extremely explicit construction. So maybe by showing that an intuition holds uh, for the existence, for the existence of an object, it's like, okay, this is enough. But people from the constructivist current will say, no, no, this is not enough. For demonstrations that kind of existence, you have to actually be able to build that whatever way possible, at least one way. Okay. So yeah,
Okay.
yeah. Carlos, you can, if you want, you can begin.
Sure. Yeah. I'll start. I would. Yeah, I would say I fall under probably more of an intuitionist or operationalist in how I perceive mathematics. I think it is hard for me to imagine that mathematics is really something more than agreeing on a set of rules and set of procedures that one recreates mentally, either because you can see them in the world, that you can instantiate it mechanically, so to speak, or because you believe it, like language, like verbal language. Um, and then it's a matter of kind of how you feeling that day to think that there's this metaphysical or assumptions or some the ontology of these ideas and things like that. So I in some sense, like I don't see the spectrum in a way from my point of view. I totally agree. There's a spectrum in terms of what ideas have been proposed historically, but from my point of view, I don't really see a spectrum or like an axis where one should position themselves. I see more like, is mathematics, I mean, is whatever you're doing, maybe you call it mathematics, useful in whatever context that is? Is it useful for the cognitive activity that you're doing with other mathematicians? You might call it proving theorems, right? And so if it is, then that's kind of the verification system. Of course, you can build a computer to have that verification system instantiated mechanically in the world, or you could do science, right? Where you build a mathematical model and you say it is verified when I see a physical system that is behaving like this mathematical model is predicting, right? For me, these are all kind of similar systems. I mean, they have different substrates, and culturally and historically, especially in the West, they are very separate. Like someone deducting logically in their own minds is a very different thing from like going to a particle collider and looking at some statistics of like interactions. But for me, it's not so different after all. If you like abstract a little bit what the agents are in the game and so on. So yeah, I would say that just in the beginning, not to make it much longer, that I tend to see it more as a mathematics as a practice and as an efficiency of a practice more than, I guess, because I'm never too interested in getting into, okay, what is there really? Is there, the ontology of things? Does it really exist? What is the number three? These kinds of things. Like, I never got too seriously into that. So yeah, that would be my first.
Good. That's great. So I will say that that's kind of a functionalist
Yeah,
approach. Yeah, and yeah, just brief comment on my side. I really think that there's this risk always to fall in this kind of too abstract debates in not only mathematics but of course in general.
yeah,
Um, and one thing that comes to mind as an example is what you just said, like what is the number three? In neuroscience, from philosophy and mathematics, of course, we are
yeah,
drawing the debate from there. But in neuroscience, there's this traditional side saying, oh, the concept of number, like animals being able to count and so on, require that they have this abstract concept of number and blah blah blah. That like fishes and any kind of very quite simple animal can count. And maybe that doesn't require like an abstract conception of set theory or whatever. So yeah. So yeah, there's always this need to have a functionalist approach sometimes because at least sometimes. So I guess well, Daniel, if you want.
Oh, yeah. So I have a similar opinion. I try to bring this concepts a little bit closer to earth because they are so often disconnected from pretty much anything, and it's just kind of like its own game, its own simulacra. But I think independently of whether you consider demonstration within the context of mathematics or within the context of science, I think the key thing is that it is about establishing trust and establishing trust primarily through repetition. So in the scientific realm, when you establish a phenomenon that repeats itself over and over again, you can predict it. And then you trust that it exists, that you can expect it in the future, or you can manipulate the settings so it happens again and again and again. And in a similar sense, I think that happens with mathematics when you take trustworthy steps and you compose them, you're essentially establishing a system that is repeatable, and then it gives the same result over and over again, and then you trust it more, essentially. And so I think in both senses, it's pretty much about trust through repetition, pretty much. And yeah, like I think connecting to the topic that you were mentioning before about like, oh, what is number three and all that, I think like, okay, initially it can be about that, about establishing trust through repetition. And I think that's probably the most practical way in which you can think of proofs. But then when this trust is abstracted, you can project this trust on pretty much any consistent system that you can establish. And I guess that leads to another question that is perpendicular to the demonstration thing, which is the relevance question. Because you can represent the number three as tally marks, or you can represent the number three as sets, and you can do it in the von Neumann way, you can do it in the whatever other way, and whether that's relevant for you or for whatever purpose that you're doing is a different question. Yep, that's it.
Great. So and then Fanny.
Yeah, I guess my thoughts aren't that well formed, I guess. I was going to say something like that I too, for diversity of opinions, I guess, was thinking similarly to Danny and Carlos. But like I guess to take a different example is that or some anecdotal example. Whenever I talk to people who aren't like technically or scientifically inclined,
Mm.
the doing deduction or induction or any kind of like logical reasoning or something like it is often seen as a limitation, or in some sense, not you're not going to arrive at certain truths or certain ideas if you only use that kind of tool. At least that's the view I often get portrayed, or I often see or come across. So like, instead of I find it difficult to put myself in that position, but I was going to suggest something similar as the others, as being more like, what's the word, sober about it or something, and like thinking about what is essentially what are for proofs and other scientific ideas. Essentially, like they only demonstrate what is fruitful or not fruitful to pursue, and basically thinking about it in that way. So it's basically some cultural search and memory mechanism or something, which allows you to not pursue certain ideas or to pursue them. But yeah, other than that, like on this dichotomy, I didn't really have any more thoughts on this. I have some other ideas about some more technical things about it, but not on this dichotomy, I think.
One quote here. So one quote from actually before I was mentioning other traditions. So from the Buddha actually is so when you have been hit by an arrow in the chest, you don't ask yourself whether God exists or whatever. You just want to finish suffering. So this kind of practical attitude, I think, it can be quite healthy in the sciences. One thing that for you all to think about, so about related to this dichotomy, um, which made me think that maybe it's interesting to for practical purposes in the sciences, is the following. So in general, in statistics, as I've become more familiar with statistics, I've seen that it's so common that some statistical tests for whatever, like NOVAs or t-tests or whatever, some of them are more useful than others for some kind of depending on the conditions, depending on what you want to infer and so on. And one very interesting thing in computational neuroscience, that's the thing that I mentioned before, is that when you are thinking about a computational model, which is usually like a mathematical equation, trying to oversimplify how the brain works, okay, you have usually, for example, like behavioral data, okay, and you try to feed the model to that data. Before doing that, when you are designing the model, you have there's a great danger. You are working usually with a differential equation with several terms and so on, and you think that you can simulate in your head. You think that you can have an intuition of how that kind of specific equation is going to translate into a behavior. So when you, for example, when you generate synthesized data, synthetic, sorry, data from this equation, you know that you are going to get this kind of behavior and not the other, and so on. And when you change it a little bit, then when you tweak it, then you're able to change in this way and so on. But there are several papers saying, methodological papers saying, no, you cannot have that kind of intuition. You need to simulate, and you need to simulate a lot. So that for me is kind of interesting, because to me this dichotomy relates to this, because the realism, like Platonic stream of thought, will be okay. Our intuition is enough for assuming what kind of behavior our mathematical assumptions are going to have independently and in relation to and in combination and so on. So, but the constructivist side will say no. You need to actually be able to build the object. be it a car or a model or whatever. That would be like the engineering guy saying, okay, your theory is great and seems extremely consistent and self-consistent, but the real world is not necessarily holding your assumptions or adding extra or whatever. What do you so having said this, what do you think about this dichotomy about and how can it be useful for discussion? Because in mathematics, I think there's this kind of debate between intuition and actually being able to build something is quite deep. And of course, it depends on the moment, the practice, and so on. But yeah,
Yeah.
go on, Carlos, if you want. Yeah.
Yeah, I'll take it first in the same order. I think that there are two main meanings that one can take in the constructivist approach. You can take it more materially in some sense, especially nowadays. This makes a lot of sense with computers. I mean, computers arguably have existed for thousands of years now because I mean we have evidence, archaeological evidence of things that are doing computational-like things for many years, but more literal machines that are kind of perceived as autonomous are definitely real today. And so you can think of constructivist in that way that, you know, I don't think we are that far off from a world where you have generations of mathematicians living in a world where there are oracles that are this infinitely verifiable machines that can, you know, you can tell when there's been an error. But if there's not been an error, you can tell that the logic was flawless and therefore and always finite by construction, you know. And so anything that you do mathematically can be verified in these machines, and we're not very far from that reality. And this is actually true for some areas of mathematics already. Like they are fully formalized, and we have like you can download the oracles in your computer, and you can know this already. So, but then there's another sense in which you can speak about constructivism in mathematics, which is more to do with the fiction within the maths itself, right? This idea of asking about existence and you know proving existence either say by you know by contradiction or by constructing an example, right? This is two ways in which you could prove existence. It doesn't mean that that you're somehow negating the philosophy of constructivism if you're using something like you know reductio ad absurdum. You know, like it might be that you're using this within the context that you have enough detail and enough understanding of your rules that it is a finite procedure that just allows you to argue and you end up with in a finitary process you end up with an answer to your question, which didn't construct the object, formally speaking, but it followed a finitary and verifiable process by in sort of a human scale, right? You didn't invoke some infinitary construction or some kind of, you know. So I think that those are the two settings in which you can invoke constructivist ideas, and I think both are very similar in form, but they are very different in sort of philosophical standing, right? Because one is about the real world and having something that is not a human mind, and the other is about how you do the mathematics themselves with the maths rules, right? So just to highlight that, I think it's important to keep in mind.
Very nice. Thank you so much. Yeah, it made a lot of sense. So Daniel.
I'll just skip the turn. I'm thinking now. I'll respond later.
It's fine. Yeah. Do you want to go, Fadi?
I was going to say the same thing as Danny.
Okay,
Can you repeat the question?
Carlos brought a very good point, but I just didn't.
Yeah.
Yeah,
Can you repeat the question so I
something
can connect back maybe?
Oh, like my intervention from before Carlos, you mean? Yeah.
Not the final question that led to this thing, because I'm trying to like piece stuff together.
Yeah, that's what I was referring to. So that like the thing that I gave as an input to all of you in this subsection.
What is it?
Yeah. The comparison. So, one of the possible connections of this very abstract debate to actual practical uses is this debate in computational neuroscience about models. About okay, if you try to build a model you may think that your intuition about how it's going to behave is great, but maybe it isn't.
Mm.
So you need to actually simulate it.
Okay.
So
Okay.
to
Then
take simulate, yeah.
yeah, I think then the question, I'm not sure if this is exactly what you're referring to, but I think the question is about reliability again, or validity, actually. Not reliability, but validity, in the sense of okay, you can make up like a board game or something. You can create Parcheesi or whatever type of game, and it works that specific game, but whether that actually corresponds to whatever else you want to use it for is a different thing. And that's, I guess that's the thing with mathematics, is that you have these two worlds. You have the board game, card game world, pure mathematics thing, where like everything is just the way you have defined them to be, and then the actual practical thing, the application, where you're actually using it for something else. And so I'm assuming that's like the actual issue, and the issue there is actually establishing the validity of constructs, which is also relevant in like other fields, not only mathematics, but also like psychology and all that.
So will you say then that like validity and validity and reliability is is there an association between those and a specific association, I mean, between those and this dichotomy? Do you mean that?
I think the question that you were making was intimately related to validity, and was probably solvable through establishing the validity of the construct, and the validity through like the association of the construct to other observations and other systems, blah blah blah, all that.
Yeah, that makes sense. One of the words that is quite, I guess, more frequently used in mathematics than validity, but it's intrinsically related, is consistency, and Danny mentioned it, yeah, and that's important. That's I also mentioned it before. If you think that you have a very consistent system, for example, one that is not you can say that exists thanks to it having overcome the proof by contradiction. I mean, like passed that test, that's to say. The thing is that, yeah, you can also reach you can also test that a system is very self-consistent if you actually build it and it doesn't fall apart. If you actually build it and it's you can then very explicitly say that, I don't know, this rocket is not getting to where it was promised that it will get, and so on.
Yeah.
Yeah.
Then we're going back to the same thing, which is establishing trust through repeatability. So we want this to repeat over and over again, and that's why we want the system to be consistent.
Fadi, do you have anything else?
I mean, I guess it doesn't necessarily only have to be consistent. Like you can even make it less restrictive and just say it just needs to be practically useful. Like for a lot of things, you don't need to even know whether or not it is consistent or correct, or whatever form you would choose there. But just, yeah, it's very hard to like fight against practical usefulness, I guess. But yeah, I don't really have many thoughts in this direction.
Wouldn't you say
Yeah,
then? Yeah, go, Danny.
Oh, but like I think it's kind of so in the realm of mathematics, you would typically see something that is you want the best criteria to like have something completely consistent all the time, and then as you go into the sciences, you start to use statistics and all that, and because you cannot prove something that is completely like that, because you're using just some defined sample of data, and then you're making inferences from that, so you have to use statistics. So in that sense, it's not necessarily that it's completely consistent, but it's sufficiently consistent with respect to some boundaries, some test boundaries.
Yeah, it just happens that that's very useful in most cases.
Well, wouldn't you say that there's a difference between, like, in terms of trust and in generated trust in
I guess I,
go, go.
you don't necessarily need consistency to have trust, I think, in a system like that.
Why do you think so? And then what will you think? What will you need?
I mean, ideally, you would want to build trust in that sense, but you can just you could just ignore the fact that you need to trust it, I guess, in that sense.
In this sense that maybe like the community is not going to be right about the problem, and maybe
Yeah.
these few people are
And
right.
and they might still pursue it, and it doesn't necessarily mean you don't get results after. So I think something like that, yeah.
Yeah.
Okay,
This,
yeah.
yeah.
Sorry.
No,
Okay,
it's
I can
fine, it's fine.
see, I can see, okay, the value in what you're saying, even in mathematics. So like usually you find some, you study mathematics, you find some exercise. So how you have to prove this. And so initially, many people are like, okay, I have to like start from this and then like blah, 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 and do it like a computer, blah, blah, blah. But most often it's actually more useful to not start by being rigorous and actually making some nonsense in the sense of or maybe the thing you have to prove is too complicated, so you actually take a simpler problem and you actually prove that problem that's easier and more intuitive for you first, and then you use that the intuition from that small problem to solve this other one that's more complicated and all that. So in a sense, you're being less rigorous, and you're kind of like exposing yourself to different short pieces of data that eventually gives you the necessary intuition of the problem to solve it.
Yeah, but eventually
Rigorously.
you would still like test it for its consistency after the fact.
Yes, but it's still useful that that phase happened before.
Yeah,
and you wouldn't get the formal proof otherwise if you don't actually do that, or it would take more time, or it'd be more difficult.
I will say that it's very nice because I think both your interventions are like showing that we need two types of concepts. Actually, now it's Alex again with his dichotomies, but the thing is that what Fagi's intervention, for example, like Daniel's intervention was interventions were great at defining how valid, like how and why validity is important. However, Fadi raised the idea that maybe something is extremely consistent, but consistent in terms of what we were saying, that is basically like we can build a trust in the community, and this is a very like we can repeat something and it will be as expected, and so on, so on, so on. But at the same time, sometimes that it's trusted by the whole community, and that we can repeat this term and everyone knows what it is, and so on, can be can be not the main like maybe it's not the main priority, because sometimes it's better for some people or a few subsystems to get to a new level of whatever, theoretically, experimentally, and whatever, and then it spreads as a virus or in any other way. Danny mentioned maybe this is some kind of be like two phases that are required in research. I think that, so first of all, yes, I think that these are two natural phases in research. I do think that since research is a cycle, then it's not that one is before the other, because of course it's a cycle, I will say, and it's parallel. It's like two parallel things that we need to cycle through, I guess. One very interesting thing here, though, is that I will like, at least from psychology, and I love getting into psychology with this because it's very intuitive, to, at least to me, to explain this dichotomy in psychology with psychometric tests, such as intelligence test or which Barbie are you in BuzzFeed, in one BuzzFeed test, or which kind of pizza are you? These kind of things may have two types of statistical value. One is validity, that is usually related to consistency, and the other is reliability. So I think that what we were calling before consistency, at least in the sense of something that is repeated across the community and is like, okay, we know that we mean this and so on and so on, has some flavor of what psychology means by valid, but at the same time, it's also reliable. And what Fadi raised, like the point that Fadi raised, was more in the sense that saying, okay, of saying, okay, maybe this is reliable, but sometimes it's not that. Sorry, maybe sometimes it's valid, but it may not be useful for some things. So, for example, a psychology, an intelligence test, for example, can be very, very reliable because it always measures in the same way people, and we get this IQ distribution in the population, in this population, and in any other sample. But maybe it's not telling us a lot about what intelligence is, and it's not correlated to what we think that it's measuring. Like maybe it's not measuring intelligence, maybe it's measuring something that is correlated with intelligence, but not intelligence itself, as to say. So I think those are two kinds of needed trusts in the community. Sometimes one or the other is better. What do you think, Carlos, about this in math? Do you think that in math this kind of debate of validity and consistency versus reliability is something that you have felt in your practice as mathematics or talk to others?
Yeah, I don't know if I've seen it that much in practice, but it is kind of an assumed reality that, and I certainly have characterized it myself with colleagues and other scientists, not just mathematicians, but people who are sort of dealing with mathematics as a thing, that the reliability of mathematics and this repeatability, this machine-like character, is precisely what makes it so powerful, right? And precisely what you can. I mean, we've built our societies around this, so it's not an alien concept, right? Like it's for sure. Like when you try to be very formal about it and very philosophical, you can get abstract. But we literally built our societies around this idea, right? In the sense that we know that the systems are imperfect and that at the end of the day there's accountability and like responsibility for individuals and all that, and like the legal systems are usually implemented that way. But normally the norms on top of the legal system, right, the things that when they break you need the legal system to come to the rescue, those are normally machine-like. They're normally like rigorous in some sense, right? Like they tend to be in their form, not in their application to reality, but in their form, they tend to be sort of self-consistent or complete in some sense, right? Like if they don't, we think they are broken, right? We think they're not good, which they're. It's not that they are completely useless; they are incomplete, and they are. But a person reviewing it will say, "Oh no, there's a loophole here, like there's something wouldn't, like this case is not accounted for. What if this and this happens? The machine has no output, right? Like the system wouldn't tell you what to do, right?" I think it's an extremely intuitive notion, and I think in mathematics people just assume it. I mean, they don't even think about it, right? Like we just say, okay, this is what mathematics is, because you're being taught since you basically become a human, right? Like when you're young enough to be able to tell symbols and tell sounds. I mean, you're being bombarded with these kinds of systems, right? Like the toys we play with all the technology around us, language. I mean, verbal language is very strongly formal in the sense. Grammar is consistent. When we all feel cringe when someone is speaking a language incorrectly, right? I mean, that might be one of the most kind of basal and kind of what is the word, visceral reactions to this formality, right? Like just the sense of cringe and discomfort for hearing someone that is, I mean, you understand the message. Why does it feel weird when someone is speaking incorrectly, right? It's because we have an ingrained sense of formal correctness and consistency somehow. So I would say in mathematics, it's kind of it's like asking, what would be a good analogy? It's like asking, like a sailor, what they think of the saltiness of the sea or something like that. It's like, in some sense, they are the most qualified person to tell you about the saltiness of the sea, because they're on the sea all the time, and they have the smell and the flavor in their skin and their mouth all the time, because they are dealing with. But they're on the sea to do other things. They are not on the sea to like taste the water and see how salty how salty it is, right? So this is kind of the analogy that I would use for mathematicians. However, I would say as a note myself that I have personally characterized mathematics like that a lot, and kind of like pulling back a little bit and realizing, hey, look at what it means to be rules based and rules oriented, and notice how this is not always the case. Like, you go out in the world, and there are patterns, and there's some repeatability and predictability out in the world, but they're certainly not rules based, or at least not in the whole scale of the phenomenon that we observe outside, right? But humans are extremely good at this, right? Like, we've so far, and with this, like, maybe I can like wave the flag of the origin of life problem for in a completely different context. But we seem life seems to be the only system that has done this, right? Like, that has sort of evolved into a position where we are organizing the world around us in this formal driven way, right? And if we got the Michael Levins of the world here, they would be saying, oh, that's because they're actually borrowing from the Platonic world of ideas, and they're bringing it into, I mean, maybe not as cartoonish as that, but like something like that, right? So I think it is an important feature, that in my opinion defines what mathematics is. For me, mathematics is doing that. Like, when you can restrict yourself to a domain that is sufficiently rules based, and you can have uh, derivations and sort of mechanical flow. It doesn't have to be complete. It doesn't have to be total. It doesn't. I mean, all these properties that people have cared a lot about in the history of mathematics and the history of sort of philosophy of logic and things like that, those are not so important. But the fact that you can operate within certain regimes where those things are true, um, in my opinion, is what makes mathematics. That, to me, is mathematics. That doesn't have to be with, does it look like algebra, or are you using logic? Is there a sense of truth, or of something being true or false? Like that to me is kind of particular examples of that feature, right? But the feature to me is, can you be rules like and consistent? And so my answer to this whole question that you were posing is, to me, it's a definition of mathematics. Like that whenever you find the context where you can be like that, be it verbally, be it with machine, be it with like rules, societal rules, or whatever it is, um, I would say that mathematics is operating. That to me is the mathematical realm, right?
So before changing to the next subsection, and I'll let Fadi and Daniel answer to this, if to this intervention, if they want. But I will very briefly say, well, first of all, amazing intervention, very well connected. I think that's I think mathematics. I wouldn't say that mathematics is entirely that, but I will say that the core and the main goal of it is that. So like, if mathematics is several things, that's the thing that has more causal power in the practice of mathematics, I will say. So that will be like my slightly, like, yeah, a small rephrasing of that, but I think we agree on that. So I will just say, so the other side, as to say, will be like one of the other complements to mathematics will, I think, will be okay. maybe this system of rules, I'm going to build this system of rules to be able to work in these contexts and so on. But wouldn't you say that sometimes mathematics is also about, okay, I want to be able to do this. I want to be able to do these kind of transformations. I want to be able to connect this input to this output, but I don't know why. And with this current system, I cannot do that. So I have to build, I have to change, I have to break rules, and temporarily at least I have to break them in order to kind of at least intuitively build what I want to build. And then yes, work on the specifics and maybe of course like building an entire new system. But in any case, that entire new system of rules is the one that allows me to do this kind of transformation. In that sense, it's not just like and connecting to life, for example. Life is not only building a system of rules and applying them, but or better said, like like constraining itself, as to say, and being reliable in applying that, but also finding the way to transform, finding the set of algorithms to do a transformation that is like selfishly wanted, basically. Yeah. That's it. So Fanny and Daniel can say whatever, and of course Carlos one last intervention also, and then we change the subsection to another briefer than this one.
Yeah, and I will say just as a heads up that I will have to go after this one because I have a meeting at 30 past. So just to let you know that I'll just disconnect at the time.
Thank you for saying
Okay. I guess the rules that Carlos was talking about, I think that they're mainly for the practical purpose of giving a sense of orientation, in the sense of you're using the rules as composable items, and these composable items which you put your trust on because they either feel intuitive or for whatever reason, or you just postulated them in an abstract space, so it's tautologically true, blah, blah, blah. But they give you a sense of orientation, which allow for maybe, as Alex was saying, to create a space that you selfishly want to create in the abstract, but also maybe the validation process is also empirical in the sense of well, this leads, for example, leads me to create a machine that works consistently and the way I want to, or it's a good model of reality, so I can make very good predictions or whatever. And I think it's like these two things, let's say the real world and whatever you want to do with this set of rules. I think these two things kind of, I mean, in the real world, in an evolutionary sense, what you want is homeostasis. And I think this idea of composable items that work as rules that give trust and a sense of orientation and all of these things, these are in essence a set of tools that facilitate this homeostasis in a way that's graspable intellectually, and in a way that you can manipulate and work with, which I think is basically one of the principles of intelligence, is this. And yeah, arguably many of these rules, they evolve as they're basically prejudice that we have from evolutionary times. We just developed this principle of objects, which are maybe related to our gestaltic understanding of the world, where we separate objects from the background and all these things, whatever. They have this ecological use and validity in the sense of we use them for our orientation, our intellectual orientation.
That's great. Fadi?
No, just want to say that what Carlos said, especially the part about basically self-correction, is like a very powerful feature of a system like science or even social systems, I guess. Is the fact that they self-correct, and that is what makes them rigorous, is the fact that they do that.
Thank you so much for these sorry, for all these interventions, because I wasn't expecting that we connected, thanks to Carlos, with the evolution of life and societies as a law systems. But I do think that it very, very intuitively links to these kind of debates. Sorry. Yeah. Now, by the way, I'm sorry, Daniel, because before I was using the countdown for Fadi instead of your countdown. Well, sorry to Fadi, I guess, because I was taking
Yes.
it from him, but yeah.
No, but that's all okay, because now when I go, it's like in a in a multiplayer strategy game, when the player loses, like all the resources get split in the remaining players.
Yeah.
Exactly. But yeah. I was, anyways, I was restarting the counter, and since I was not using it that much, because this is one of the things for this kind of meetings, since if first of all it's flexible, secondly, if in the end we are not that many people, we can rearrange this. And this, of course, I'm also talking to the audience when saying this. Just think of this as a very flexible, moderated environment. Okay, so where you are very welcome to come, and you will not be forced to intervene immediately if you don't want. As you've seen, I've let some space to the speakers in case they wanted to think more or whatever. So yeah, basically now for the last like 10-15 minutes, whatever. What I want to so there was another like sub question, as to say, that I wanted to for you to delve into, which is, well, one of them, at least, because I had several options, but one of them is okay, let's say that there's a long-term assumption, long held assumption, okay, in mathematics, any kind of science. That long held assumption is extremely terribly wrong, but it has been believed to be correct. Okay, and I'm just, by the way, I'm as I'm pronouncing these words, I'm just realizing that we were talking about this before. So the previous interventions were already addressing this question. So basically, the idea was, okay, yes, this long held assumption is very wrong, but it was correct. It was thought to be correct, and it may have been useful for science, because at least there was something that people assumed to be correct, and then there was some non-infinite chaos to their lives. So maybe even if it was wrong, it helped knowledge. Okay. So the thing I wanted to bring to here is, so first of all, there's this thing about demonstration that is, at least in principle, given this story that I just mentioned, this like historical idea, demonstrating something is not that immensely important for the development of science and mathematics, because maybe in the long term, what matters most is being able to develop the fields, even if they are not developing in the right direction. Of course, sometimes there can be like very extremely wrong directions, and that lead the field astray for centuries. But I'm doubting about whether this is that important for cognitive systems that are very flexible, and that anyways they'll reach a point in which they will be a little bit more optimal than before, whatever path they take. Especially when we think that when we know that many paths converge to the same direction, even if some of them are maybe wrong or right in the specific local historical context to the people that inhabit them. So this brings the idea of the doubt whether of until which point is useful giving importance to demonstrating things, both in mathematics and in science. And this is quite a controversial question in some regards, of course, in both areas, but yes. And how much we should take into consideration that something is applicable everywhere and so on, because maybe it's not that important. And then, of course, this has a lot of implication in defining the frontier between pseudoscience and science and so on. You can go into that place. It's an option, but yeah, it's not only that. It's more also about the very local daily scientific practice. So yeah.
I'll say something quick because I have
Yeah,
to
no,
leave.
of course, I was going to give you the
Yeah.
because
So I'll just a thought briefly. Unfortunately, I won't be able to like address the broad topics you just described because I think they are very interesting and I don't have the time. But just to give one thought, maybe useful for listeners and everyone who is thinking about mathematics in this level. You refer to this idea of universality or sort of exportability of how much you can go around with something that you proved or demonstrated somehow, and then like it has sort of ramifications beyond its own sort of original um, sort of domain, right? So I think intuitively one can think of even the concept of number as being one of the most intuitive manifestations of this phenomenon. So if you think about what numbers have been used for historically, especially before modern mathematics or modern science, numbers, if you think about it, are extremely universalizable vessels, right? They were mostly used to do some kind of, early exchanges and early commerce, right? Like that's what numbers are, believed to be likely to be coming from, right? The fact that you wanted to say that, two sheep equated whatever 10 apples or whatever, like there was some kind of countability. I mean, the world, especially biological world, is very countable, right? It's made in units. And the idea of counting with numbers, and of course, this then generalizes to measurement in general and like defining, uncountable things like water and, things that are sort of continuous, so to speak. The idea that you can talk about arithmetic in the abstract. I mean, obviously, historically, no one was doing arithmetic in the abstract. They were looking at their hands and like counting with their fingers, or they were, having some kind of, or looking at bits of grain and like, taking them in like 2 bags and things like that, right? But the conclusions that you got by doing, I grab these 3 bags, I put them together, I can't have enough for now, like the rest of the season, and all these kind of like necessity-driven computations, they were completely exportable to any other thing that you could count, right? It didn't matter what it was. It didn't matter that you were counting, the number of moons that you saw in the sky before your child was born, right? Like this is completely different from counting grain to plan for the season for food, right? Like, and however, arithmetic was totally the same, right? Like there was no feature of the system that was relevant for the arithmetic just having the same rules. So I just want to bring this example because I think it's so ingrained in our culture that it's sometimes hard to like go back and revisit it and sort of rethink it. But if you think about arithmetic, the rules of arithmetic that we all learn when we are 5 or 6 or whatever, it's so platonic and pristine. It's so disembodied, right? But it's actually a physical model, right? Like those rules are a model of reality that you can go and verify that 2 + 2 = 4. Like you can verify this statement. It's not empirically, right? And the great power of arithmetic is that you can verify it in so many different settings that as long as you have a sufficiently acceptable definition of number in your setting, then arithmetic is going to apply, right? As far as we could. I mean, okay, this maybe breaks down with in quantum mechanics or something like that, where things start to like break down a little. But in general, for all our experience, this has been true even all the way to modern physics. Like as long as you don't get into some other realms. So I just wanted to bring it as an example of that sort of exportability and universality of things. That even the simplest thing that we all learn is arithmetic already has a very distinctive feature of that. So yeah. It's very nice. So I thank you, Alex, for organizing this topic. I really enjoyed it. I hope you guys have more fun here. And to all the viewers and listeners, I'll see you in some of the next Concept Colliders. And I'm sure we'll have some more participants as we sort of keep circling the topics of the summer school. Also we'll be announcing soon some of the speakers are already confirmed, and we have some good news. So yeah, thanks a lot, everyone. Fadi, Danny, and everyone at home. See you soon.
See you.
Bye-bye.
That's probably the case, but still, it's very interesting that even when it's not about counting apples, you're still using like the sequence that are most used are the same. So that means that maybe our concept of mathematics is quite valid because it's quite consistent. Because yeah, maybe it may not make a lot of sense to say that counting is in the same field than differential equations or whatever, but or category theory or whatever. But it makes sense apparently, and it's interesting for me. Aside from this anecdote or from neuroscience, it's interesting because maybe it's why Carlos what Carlos was saying holds. So maybe it's not that necessary to define what a number is and decide between set theory or whatever, or how to build the integers. Like are the integers empty sets, uh, like into like within empty sets, and that's how we build the integers. Or is there any other better way or whatever? Maybe those things are not that intrinsically necessary for doing mathematics. Maybe because like the most essential thing in mathematics is just numbers and counting. So maybe we don't need to go that further, that far with them, because they are our not like they are our, how to say, our main assumptions, but not in the sense that we need to reveal them to be able to practice mathematics, but in the sense that they are quite independent from our specific practice. And since they are quite independent from our specific practice of mathematics, then we can rely on them, regardless of what we think that their foundations are. So it's different from thinking that assumptions are just what we need to work to do some job. It's that precisely them being so independent from our practice makes them safe for us. And with this thought, I give you a thought, Danny. Yeah.
Okay. Okay. Two things. So first, you were talking about it doesn't matter whether like number 3 is this or that or whatever. I think it's in mathematics, it's probably more useful to think of things in a more horizontal way instead of a vertical way. Like usually when you talk about foundations of mathematics, it feels like you're talking about what's beneath everything. But I think it's more useful to consider that, okay, 3 can be this function applied 3 times, or or 3 can also be this set of empty sets or whatever. Okay, so you have all these considerations, probably not so important, every single one of them, but there's the possibility that a specific instantiation of the number 3 is more useful in a specific case or specific situation, even for the purpose of understanding the problem or getting some insight on the problem. For example, if you gather, I don't know, data from like 500 people, and you have a table, and the table is full of numbers, blah, 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 like that, it's not really useful for you maybe to go there and just read the numbers out loud. It's not going to give you any insight whatsoever, or it's going to take a long time for you to actually grasp what's happening. But if you plot it, then you see a curve and you're like, oh yeah, okay, there's this variable and this other variable, and they're related with this linear whatever, or like parabola or whatever. And, there's this relation. And that's a way of, let's say, manipulating how the information is presented and how we're looking at it can give us insight and actually help us solve problems in a different way. And so I'd say yes, it's not so important how you're exactly thinking in general about the number 3 or whatever, but it can be useful for specific purposes too. And probably some things are more useful generally. A graph is very useful for many purposes, many different purposes in science. Maybe thinking of the number 3 as sets of empty sets, not very useful in science, but maybe in some other context it is. I don't know. I'm not going in there. But yeah, so that, and then the second thing I was going to talk about is, because you earlier talked about things that are not necessarily like, I'm trying to connect with your question exactly what it was, but I think it was something like sometimes it's not necessary to demonstrate that something is true, or that we can work with a model that's false and it can help you. And I think that's probably like the history of science, really, because like we've been constantly proving ourselves wrong, but we're just becoming less wrong, relatively less wrong. And this way in which we're becoming relatively less wrong, we're able to predict more stuff. We're able to do so much more with better models that are more general or more fitting. And I think what you were saying earlier also connects to negative results in science, which is really important. Of course, you don't only want to prove that something is a certain way, which of course it's great. It's great to have that, but it's also very important to know what is not the case, what is not like that, so you can actually avoid researching that over and over again to begin with, of course, but also it refines other models, because you can say, okay, if this is false, then this other model probably also false, because they're very close to each other and almost the same thing or whatever. There's some causal relation between them, some implication. So yeah, sometimes a model, even if it's false, it's relatively closer to truth, or it's somehow orienting you in making choices, or it's giving you a heads up, really. Yep. So that's it.
That's great. That's great, Daniel. That was great. Fadi, if you want to.
I had something to say and then I completely lost it while Carlos was talking, and I've not been able to think back to it again. So I don't.
Is it related to numbers, or
No, it was definitely not related to numbers and things like that. It was a very general statement. It's not related to what Daniel's talking about right now.
Okay.
Okay.
Yeah, like
So,
I
well-
usually write them down because I get
Oh,
lost
yeah.
as well.
That's actually something I should. So what was the original prompt again? Maybe I'll think about it again.
That's why that's also why less papers may help like another kind of maybe controversial claim, but less papers may help our research, but because maybe if we speak less, we can actually remember when we were going to study
Yes.
before we began reading. So
I agree with this. Yes.
Yeah.
that happens to me a lot. Yeah. Um,
It usually doesn't happen with me, but I just completely lost it.
we said a lot of stuff. So
Yeah, it's just
in case well, in any case, if we when we go back to this topic, because we will, like, we are
Yeah.
cycling
yes.
like I said, I remind the audience we are cycling the three topics of the summer school: cognition, rigor, and causality. So when we go back to this topic about rigor, and we will definitely speak again about demonstrations and stuff. So maybe Fabio can do the intervention.
Yes. Certainly. I'll save it for next time.
If he remembers after all the people like he daily speaks with, keep talking like in spite of that, until the next concept college. So thank you so much for coming to this event. This had so much fun. It was way better than I expected, to be honest, because I mean it's always better than I expected, because sometimes I also feel like not only the people that join like as you two, but also like me, I'm always like, okay, will I be able to
Say
draw
something.
interesting, no, yeah, and bring interesting sub questions and like create an engaging
Yeah.
conversation. But this is the kind of thing that I like about these events. Like everyone is welcome and everyone has a valid thing to say. And it's not only there are no dumb questions. It's also there are no dumb interventions, especially when we have a nice attitude for exchanging and so yeah. So I encourage everyone seeing this live or later to to join this call. And yeah, thank you so much. We'll see ourselves, like we'll see again each other again. I mean, in the end, by the end of March, I think we like the intention is to do this every 3 weeks. So yeah, the next time will be causality again. Yes, causality.
Do we have a
So
question for that already or not?
not yet, but you can go on Discord and like I will post like several options for sub questions as always, so people can vote the preferred sub question within the causality topic. So yeah, so trying to be democratic, especially because it seems if thanks to that people will be motivated for the subtopic because they chose the subtopic, so apparently they should come. So thank you so much again. See you next time and have a great, lovely Friday and then weekend, which is more important.